Okay, well, good afternoon, ladies and gentlemen, and a warm welcome to this Orkney International Science Festival 2025 event. Before we begin, can I just do some safety housekeeping? If you hear a fire alarm, can you please head down to the fire exits? That's the two doors down here, and also the door that you came in. The muster point is just outside in the car park, and if you just gather there, if everyone's deemed safe, we'll guide you back in. You just come back in through the main door and down to your seats again. Could you also do the speaker and yourselves a favour by putting your mobiles into silent mode or airplane mode, or switch them off, please? And I'll check mine so I don't embarrass myself. Just to prepare you, we will have a roving mic at the end of David's talk, so just perhaps think of some questions or comments you want to make at the end of David's presentation. Right, so it's my pleasure to be hosting this talk in the cinema this afternoon. I'm actually a very keen astrophotographer and aurora hunter. So this talk is just absolutely right up my street, and I'm looking in the audience and I can see at least 3, maybe 4 other aurora hunters, some local, some visitors. So you've got a good knowledgeable audience, David. Our speaker this afternoon is Dr David Kerridge. David spent his career at the British Geological Survey based in Edinburgh. He began by working in the geomagnetism unit and went on to manage various scientific teams across BGS, mainly those focused on natural hazards, including seismology and volcanology. He led the BGS's first project in space weather, commissioned by the European Space Agency, and helped make the case for space weather hazard to be included in the UK National Risk Register. Old people in Orkney told George Marwick of Yesnaby that they heard the shuffling feet of the dancers in the sky. But with the northern lights over 80 kilometres above us, few scientists believed it. It's only in 2012 that a researcher recorded the sound, and its mechanisms are still unclear. Today, David discusses the evidence for auroral sounds and describes the current understanding of how the aurora is created. David?
I'm no David, no. But I was asked to give a little bit of background to George Marwick. 1836 to 1912. He was born at Yesnaby, did many jobs during his life, from working in the millstone quarry at Yesnaby to land surveying, and had a go at farming, not terribly successful, though his father got a lease of the Boo in Hoy, which Geordie didn't have much of a hand fist at, because he spent most of his time heading off between the hills to go to Rackwick to speak to old people there and hear stories and customs, and which he would then write up, and he would give talks to, like, the Young Men's Mutual Improvement Society in Sandwick, and then that would be republished, that would be printed in the Orcadian later. And so that's where a lot of these stories come from, as well as papers from all over, which was gathered together over a long period of time and published in 2014 under the title of George Marwick, Yesnaby's Master Storyteller. You can buy it in bookshops, and all the money goes to the Heritage Society for the royalties. But Geordie himself was a man, like I said, collected stories, collected customs, and also just snippets of information that he got from old people as well, like the stories of the merry dancers, as we call them. In Shetland, they call them the merry dancers, which makes more sense to me as an Orcadian with very elderly parents when I was born. So my dad was born in 1911, my mother in 1922. And to murr, for anyone that doesn't know, is to vibrate or tremble. So you said the cat was murring because it was purring. And if you're carrying something heavy and then your muscles are trembling afterwards when you put it down, that's your muscles are mirroring. So the merry dancers would be the shimmering dancers rather than merry as in maybe had one too many. But if you can ever have one too many. Anyway, I shall pass you over now and go and sit down. Thanks, folks.
Thanks. Thanks for everybody for coming. One of the things that keeps me off the street these days is doing guided tours of the birthplace of one of the greatest scientists ever, the Scot James Clerk Maxwell, at his birthplace in Edinburgh. And you're all, I would recommend it, of course, that you come and visit anytime you come to Edinburgh, and visits can be booked on our website. One of the things that I found really difficult in taking people round is to put your mind back and describe the science, say, in 1860, in terms of the knowledge that they had at that time, and not assume all the things you've learned since. So I am always a little bit scared of cheating, but I'm going to have a little prelude of cheating now, so I'm going to be upfront about it, just to define a couple of terms that I think will help as we go through the story, going back to the mid-1800s. And the first thing is that we've already heard about the ionosphere. So what is it? And I listened to a talk by two guys from the National Physical Laboratory last week, so I've got a new hobby of inventing units. And so the ionosphere, looking up into the sky, is about 10 Everests up, so it starts about 80 kilometres up. And it's called the ionosphere because there are ions, and ions means that the molecules and atoms up there, or at least some of them, a small proportion, are charged. So that if in some sense you can put a battery there, it will make currents flow. And then currents make magnetic fields. And that's what we can detect at the Earth's surface. So each of us has a Moby, and in it you will have a magnetic field sensor. And so this is a really fundamental scientific concept that came from Faraday and Maxwell about the idea that you've got a localized current, but this big idea of having a field, and it makes a field that extends throughout space, and we can detect it here on the ground even though we're away from where the action is up there. So it's quite a profound idea. So your Moby is, in a sense, doing remote sensing of things up in the sky, and in a very different story, it's also doing remote sensing of currents flowing 3,000 kilometers below us in the Earth's core. Just one more concept that will help is the idea of a plasma, and that's where you have a gas where it's totally ionized. In other words, everything in it has a charge, and that'll come up in something I'm going to call the solar wind. And if you want a very intelligent question at the end, you can say, what would happen if the solar wind wasn't a plasma? Okay, so I'll seed a question that I can answer rather than one. And throughout this, I'll be talking about aurora and also magnetic storms. And for the purposes of this talk, you can take them as almost interchangeable, because if there's a magnetic storm, you're likely to see aurora. If you see aurora, there's going to be a magnetic storm. So don't let me confuse you on that. Okay, let's get on with it. So we can't start sitting here. We have Callum Potter, and so these are some images of aurora that Callum has taken on Orkney at different times, and that should surely get you enthused about the subject if you're not already. And okay, what you can do is you can either simply enjoy the show, But if you're of some kind of scientific bent, you will wonder why it happens, how it happens, when it happens, where it happens, and if it tells you something or not when this is happening. And in the last weekend, there was a meeting of the British Astronomical Association, and that itself, I guess it's full of people who have a night job, mostly, unless they're hunting eclipses, rather than a day job in the subject. But they are in the Premier League of making scientific observations, and it's still at a point where discoveries can be made by amateurs. And that's certainly true in the section called the Aurora and Noctilucent Clouds section, which is run by Sandra Brantingham, and the president of the British Astronomical Association is Janice McLean. So if you get enthused and you want to join and benefit from the knowledge that's contained within lots of amateur people who have very high levels of skill and knowledge, get in contact with them. So moving on to the main event, first of all, something about the names that Tom has already discussed. And in George Marwick's book, he refers to them being called the hurry-burry of the Allens, and then the aurora called the merry dancers. And George was a very keen etymologist, but he wasn't always necessarily that accurate. And so he made an association between the word merry and the Scandinavian words for the sea, mare or mere. But some also said then in Shetland, merry dancers is as Tom described, and I had an email from Tom, so I've repeated what he said here. And so it's more to do with the shakiness and the shimmering. So I'm seeding an idea here that in making a connection between the aurora and the oceans was maybe mistaken, or he was misled by the interpretation of the meaning of the word. This kind of presentation gives me an excuse to show my second favourite cartoon, which says, I used to think correlation implied causation. Then I took a statistics class, now I don't. Aha, sounds like the class helped. Maybe. And in about, 10, 15 minutes' time, you may hear me repeating that same punchline. And of course, as human beings, it's natural for us to look for explanations where there seem to be associations between two or more things. And that might be direct causation, A causes B, or there might be a common cause where A and B are caused by C, or there might be some effect of triggering. And these are ideas that you might want to have in your head as we go through the descriptions. So what did George have to say about sounds? I've heard old people affirm that they have heard the shuffle or noise of the feet of the dancers. I've heard an old fiddler affirm that a certain tune that only he could play, he learned one night sitting on and now looking at the merry dancers. So, the big question, are they real? And here we have a quote from John Rae, the local lad, which is very perceptive. And so he was in the Arctic a great deal, and there's some key words here that will come back as we go through, that it's occasionally audible. The natives believed it to be close to the earth. He's seen it many, many, many times, but he has never heard it. The sounds that he has heard reported are like the rustling of silk. And maybe there's something else happening, like the formation of ice spiculae and the crackling in the air. But he did say all Indians, both on the shores of Hudson Bay and near Bear Lake, and the Eskimos on many parts of the coast, assert positively that the bright, varying, flickering, and rapidly moving aurora do produce a sound. So he was keeping an open mind, even though he had seen it many times and heard nothing Okay, now with the danger of getting slightly pedantic, and you'll see why, I hope, as we go through the talk. You know, what does it mean? What does the term auroral sound mean? Does it mean simply a sound that you experience when you're seeing auroral lights? Does it have to happen always or just occasionally, as John Rae said? And what if you hear a sound without any of the lights? And something I'll make a comparison with is thunder and lightning. And yeah, when I was a lad, then I was taught, you know, if you see the lightning flash, then you start counting, you know, elephant 1, elephant 2, Mississippi 3, Mississippi 4. And if it gets up to 5 seconds, then the point of origin was about a mile away, or in new money, if it was 3 seconds, it's about a kilometre. And there's an important underlying assumption that we believe in, but it is an assumption that the light and the sound originate in the same place. Okay, and we'll come back to that. So, reasons for skepticism. And throughout history, you've had expert witnesses on both sides, some saying, yes, there are sounds, and some saying, definitely not. And the first one is, as I say, unreliability of human ear witnesses. And here it gets really interesting about how human perception works, because maybe we think, well, it's a light show, it ought to be a light and sound show, and perhaps the brain is capable of manufacturing a sound to go with the lights. And in fact, there is a term, visually evoked auditory response, a form of synesthesia. And when you think about it, then we as humans were equipped with senses. We've got eyes, we've got ears, we can feel things, we can sense temperature, we have our various senses. And it's a bit weird when you sort of think that what happens is these all generate electrical signals that end up in your head, and then somehow your brain creates the perception of you in front of me, whether there or not, and how that works. But unlike a scientific instrument that might faithfully record the data, our brains go on to interpret it, and mostly, I suppose, to decide whether we need to run away to survive. But they can all interact. And another thing about it, we've got the idea of a spectrum. We think about sounds. There are infrasounds that we can't hear. There are dog whistles that we can't hear, but dogs can, so that's interesting too. And the same in light, we can see from red, we see the rainbow colours, but we don't see ultraviolet and we don't see infrared. So in many things there's a spectrum, and we're equipped with sensors that see a relatively small proportion of that spectrum. The next thing, of course, is it something else? Is it the wind, the cracking of dry snow or ice, or even in very cold areas, the sounds made by your own breath as you breathe in and out? So can it be something else? And then there are these sort of key scientific objections, and this is where it's kind of cheating, because how did the people who were reporting these things, they didn't have any reason to know all this stuff. But it's 80 kilometres up, and so what we know now is if you try to make a sound up there, where the air density is something like 100,000th of the air density that we're breathing now, then it won't go anywhere. And even if it did, it would take several minutes, maybe 5 or 6 minutes, to get down to here. But it's not such a stupid idea, because what we do know is that there are infrasound signals, waves that travel past you but take about 100 seconds to go past, that do get from up there to down here. So it's not stupid. But the important thing here, and compared to what I said with lightning, observers are often saying that the lights are dancing to the tune of the sounds. So they're in the same rhythm, they're in synchrony. And that doesn't follow at all from the idea that it's going to take them 5 minutes to get from up there down to here and stay in synchrony. It's a bit of a stupid objection, but I've seen it written down. If you're a scientist, you can't really object that there are no scientific instruments. So if you look in the literature, and I hadn't before I was asked to do this talk, then there's a huge history of papers in the top scientific journals in the 1930s, 40s, including Nature, and a huge debate around the subject. And in fact, in the international polar years in 1882 and 1932, on the menu of observations to make was of auroral sounds. But for some reason, they didn't take instruments. They sat quietly and listened. And the whole thing was unresolved. But in 1973, Silverman and Twan wrote a 100-page paper where they tried to look at this thing obviously very thoroughly and considered all kinds of possibilities for auroral sounds. And I spoke to Mike at the top about hearing things, and he said it might have been tinnitus. So that's on the list, as well as the psychological theories, the breath, the meteorological, the direct transmission of sound, infrasound, electromagnetic radiation causing sound. But they came to a conclusion. So they concluded that the observational evidence supports the reality of auroral sounds. So they looked hard and long at this. But the most likely source of sound seemed to be a brush discharge, and these are generated by aurorally associated electric fields. Now, a brush discharge, you usually saw it, or a corona discharge, you usually associate with a sharp point at a high voltage that breaks down the air nearby and causes that kind of display. So, could that happen? Now, stepping back to 1600, there was a man called William Gilbert who wrote what many think was the first scientific textbook. And it was William Gilbert of Colchester, and he was a physician to Elizabeth I and also briefly to James I/6. And he wrote a book, he did investigations on magnets, and he came to the conclusion that the Earth is a magnet. So well ahead of his time. But he also had a great talent for a rant. And his opening sentence of the preface, clearer proofs in the discovery of secrets and in the investigation of the hidden causes of things been afforded by trustworthy experiments and by demonstrated arguments rather than by the probable guesses and opinions of the ordinary professors of philosophy. In other words, those guys in the tavern who think they could solve every problem by dint of their formidable intellects. And there's still probably a few around like that now. And he goes on in that vein for quite a while. It's very entertaining reading. And all I would say is if you come across him in a future life, don't mention copyright. Right. Okay. So, in this spirit, if you've got to find something out properly, you've got to do an experiment. You don't just theorize about it. So I contacted Professor Unto Leiner, who I didn't know before, but he's been very generous in helping me with his ideas and his publications, and in due course, sound recordings. So he started a project around 2000. And essentially in science, here he's starting with, can I detect any sounds? And then next stage, can I measure them to make data on which I can work? And then thirdly, go on and produce a theory that seems to fit the observations. So over 25 years, that's the kind of work that he has been trying to do with colleagues, of course. Sorry, button. So trigger happy. So what he has done, and closer to my own understanding, I like to think of it as upside-down earthquake location. If you're trying to locate an earthquake, you want to know where it is in 3 dimensions and what time it went off. And again, with the assumption of a point source. And so with that, what you do is you get 4 seismometers, and if you get the data from those about the arrival times, you can work out those 4 parameters. And essentially, he's doing the same thing here, very similarly, but the source is up in the sky rather than deep in the earth. And so in this illustration, there are actually 4 microphones, but the essence of his experiments now is to have 3 microphones and a device to detect magnetic field as well. And the really very surprising thing is that, I go straight to a conclusion here, that in the same sense of lightning, the delay between thunder and the lightning flash, then here he's got a delay between an electromagnetic pulse traveling at the speed of light and the sound of only something like 0.2 seconds. And that means the source is only, 70 meters away. So that was hugely surprising, because that's below the top of a redwood tree, 70 meters. So that's a key thing, that's a key point, that the source of the sounds appears to be quite close to the surface. So how on earth could that happen? Now, I've given a little reference there to a fairly recent YouTube. There's something weird going on with the Northern Lights, and that's well worth looking at, and it describes his work. And what he did is look at, he did a survey of people who had looked at the aurora and looked at his YouTube, and he did a survey and asked people what they thought they heard. And so these are some of the words that they used: ring, crack, hum, pop, crackle, static, whistle, clap, hiss, buzz, shimmer. And I found out that on the Facebook page for the Orkney International Science Festival, people had sent in comments when they saw this talk was on the horizon. And so I just yesterday wrote down some of the words that they used: clap, sing, hum, cracking, swoosh, whoosh, crackling, static, bacon frying, hiss, and swish. And what it reminds me of is a bit like when I was a schoolboy and I was banished to the attic, and which was my bedroom, and it was pitch black in there. I would come home with my brine nylon shirt and my school jumper, rip it off, and you would hear the crackling and see the sparks, and it all sounds a bit like that. So what I'm going to recommend to Unto is he gets sponsorship for his next phase from Kellogg's. Now, I went to the, I don't know if Janice from the BEAA is here. No, but I went, who's the president of the BEAA, and I asked her to do a straw poll of people sitting at the meeting at the weekend, and there were probably 70 or 80 expert observers, and we said, how many of you have heard the aurora? Put your hands up. And guess how many put their hands up? I'll tell you, none. So, how about, are there any ear witnesses here who think they've heard it? So, a few. So that's good. Consider you a success. Now, what I'm going to try to do, if I can remember how to do it, is Professor Leiner very kindly let me have a couple of sound files, and these are of one particular kind of auroral sound, and so I've got to do that once. Not what you expected, probably. And then, but what I noticed when I heard that for the first time, I thought that's a bit like banging two planks of wood together, and that is exactly what somebody said on the Facebook page for the festival. So that's, completely independent. And so he says, he called that Smith Ilmarinen's hammer. So it's quite nice that he's linking back, as we are doing here, to something that is in folklore, but in Scandinavia. And the second one then has two more of these clap sounds. And he says you first hear them in normal mode and then slowed down by a factor of 5. That's all. So when I heard those, I was quite surprised too, because I was expecting more of the crackling variety of sound. But actually, it's quite important. These ones are quite important, because if you're going to time events, you need something that's short and sharp. You can't really get timing very well out of crackles. But if you get something that arrives like an earthquake, then you can get timing information, which leads us to this idea that it's about 70 kilometres up. And so, having got that analysis, he came forward with this hypothesis of what happens. And it remains a hypothesis. And perhaps you've seen that when you get a temperature inversion layer, normally as you go up, the temperature goes down. But on some occasions, it can go down and then go up again. And this is, perhaps you've seen, so it's got the illustration here of a house with smoke coming out. The smoke rises, but then starts to go horizontal. And that's because the air above is actually hotter than the smoke, and so it stops rising. And so what we know, there's a really complicated diagram showing a global electrical circuit, and there's a constant movement of charge between the ionosphere and the ground. And the hypothesis is that negative charges rise, but get stopped below this inversion layer, and positive charges are coming down and get stopped on the top. So in effect, what you've created is a kind of capacitor across the inversion layer. Now, the big question then is, can that discharge? And so the hypothesis is when there's rapid magnetic field variations, something associated that might trigger a discharge across that layer, and that becomes the source of sound. So this is why it's different to lightning, because the light shows up there, but the effect where the sound is made is much closer to the surface. And this is why you can have the lights dancing to the tune of the sounds. There's another thing. So this explains the claps, but not the crackles. And there's another theory. If you think about the ionosphere and the ground, they're both a little bit, they're both electrically conducting. And if you thought, you can think of those as mirrors. And when there's a lightning strike, they act as what you would call a waveguide. And if you went to the quantum talks, there was this idea about how many waves can you fit in a box, which comes up again and again in physics. And it's the same thing here. So, but you get a spherical, like the shell of a football, between the ground and the ionosphere. And again, how many waves can you fit in? And if it was a real mirror and you shone a torch, then light would go round the Earth 7 times in a second. So there's a fundamental mode of 7 times a second in there. So what Professor Leiner has also done is find some evidence for correlation between what are called Schumann resonances between the ground and the ionosphere and the behavior of crackling. So I think what it amounts to, we've seen there's many descriptions of sounds. They probably all are electrical in nature, but the exact mechanism for generating them is different. So, what's the answer? So there is compelling evidence. People don't lie. They're not trying to make it up, so they do perceive sounds. And following scrutiny, it appears to have to be an electrical discharge. Professor Langer's experiments and hypotheses do this explain the key observation that the light and the sound change in synchrony, and identifies rapid changes, magnetic storms, as a possible trigger for causing the discharges. And of course, if it was something else environmental, you wouldn't expect to be able to demonstrate a correlation between magnetic field changes and something else in the environment. And so what we say is that the ionospheric conditions 80 kilometres up develop completely independently of this capacitor close to the thermal inversion layer. And so this is where I come back to my maybe and where I come back to my pedantry. So it depends on what you require as your definition of an auroral sound. So, yeah, people sometimes hear sounds when they see the aurora. Whether or not it qualifies to be called an auroral sound is still a maybe on there. But I think the observations are true. And if I was going on to a next stage, because the thing is so near to us, I would almost like to go and get a happy birthday balloon filled with helium, 200 meters long, and put a temperature sensor every meter, and also be able to measure the electric field going up. That would be really interesting, along with the microphone recordings and a camera of what you're seeing. So that would be my next experimental step if I had the money and the inclination to go and investigate this further. Okay, the second challenge to me was to link what George Marwick said about the tides. And this is very tricky. If the display comes on with the tide, it lasts that tide. If it comes on after the tide has changed, the lights are very feeble. If there is before the display a groundswell or land sea running immediately on the appearance of the aurora, the sea or swell goes down, even if the beginning tide should be flood. Now, happily, I've got some help with interpreting this, because it's quite hard to make out what the claim is and what the claim is here. And again, a second quote, there seems to be some mysterious connection, and also then bearing in mind the association he had in his own mind between merry dancers and the sea. So this, yeah, it's difficult to understand what the claim is. And they seem to be Orkney-centric, but if you see the aurora here, you'll see them in Shetland, you'll see them on the mainland, and the tide will be very different. And then where in Orkney, I mean, I looked up here the tide times between Kirkwall and Stromness, and the times of high tide vary by more than an hour. So it doesn't seem to be a very precise claim that you can test. But on the other hand, you know, these stories arise, and particularly folklore stories about weather science, and people would naturally look for patterns and significant dates as having a predictive value. And thanks to Alan Scott, I know about the borrowing days in Shetland, where the last 3 days in March are meant to foretell the weather in May, June, and July. So, I don't know. George was writing down, I guess, what people had told him. They weren't necessarily what he believed, but he was relating the stories that he had heard. And so perhaps there were a few observations where this could be said to be true, but couldn't really be extrapolated. in trying to find something that they have in common, we know that there's an equinoctial effect both in ocean tides and in the frequency of magnetic storms, but it's for really quite different reasons. And I take this chance to go back to my employer, as was British Geological Survey, and we run magnetic observatories in the UK, and one is on Lerwick, and there we record the magnetic field every second. So there's no shortage of data in order to try and test a hypothesis. On the geomagnetic side, it would be thinner on the tidal side. And again, the word tide is used in relation to the ionosphere, and you have ionospheric tides, but whereas the ocean tides are driven by gravitational effects of the principally, well, the moon and the sun, this is driven by solar radiation rather than gravity. And one of the remarkable things now is that we have satellites that are recording the magnetic field, and it is truly amazing that ocean currents make magnetic fields, and you can actually detect them now in the satellites. So it's a huge thing, because you're talking about measuring things at the level of 1 in 100,000. Okay, we're looking at the time. I'll move on quickly, and I'll tell you how science has gone on. Actually, some of this is contemporaneous with George Marwick, and how we've evolved our understanding of the aurora, essentially. And there's a very significant event on the 1st of September 1859 when Richard Carrington looked at sunspots as he did every day, and he had an appearance exceedingly rare. At points A and B in that diagram, there were two intensely bright white lights. And being a good scientist, he said, all right, I found out somebody else saw these as well, but I haven't discussed it with him so that our two accounts of this event remain independent. So good scientific methodology he was employing back then. Now, magnetism is something we've measured for a long time, and essentially based on swinging magnets. And Greenwich Magnetic Observatory, D on here is declination, which is where your compass points in relation to true north, how many degrees away it is. And we'll just stick to that. H is the strength of the horizontal component. And here, we now would identify that blip as a solar flare effect. So here, we were, for the first time, relating an observation of an event on the sun to something in the magnetic field on the Earth. And then as we go on in time, and in case you wonder, these don't line up exactly because of the way the photographic paper was arranged. They don't line up in time. But then, if you like, things go mad as something else happens, and we'll describe what that is in a few slides' time. But the magnetic field is all over the place, and aurora are seen everywhere. So we've got the smoking gun now. And this all happened about 17 hours after the solar event. So we've got a smoking gun of a big event on the sun. We see it in the magnetic records, and people see aurora even down to the Caribbean and beyond. And this was also the time of what I would call the Victorian internet. You had Morse sending signals for the first time along wires in whatever it says in there, which is 1844. And it was also the era in which, incredibly, they were laying cables across the oceans. And here, a few days after, when the field was still disturbed, there were telegraph operators, red for Boston, blue for Portland. Turn your battery off. I have done. Oh, mine is disconnected, but we're still talking to each other. How does that work? And it's actually better than with the batteries on. So the aurora was powering the telegraph lines. And in fact, some telegraph offices went on fire because of this. So, right. For a sense of proportion, and I couldn't resist the pun, but we've really learnt so much since the space age started. As I said, with your mobile phone, you're doing remote sensing, but when you get into space, you can get closer to the action and right into the middle of it in some instances. You can certainly get into the ionosphere. And that's meant to be a scale diagram of the Sun, Jupiter, and the Earth, and then an eruption of material from the Sun. So you get some idea of the sizes. And just as a fun fact, the Sun is, well, if you took the Earth as a marble, then going across the Sun would take about 110 of those Earth marbles. And if you put the Earth where it actually is, you'd have about 110 beach balls of the Sun to where the Earth is. So if you think about looking from the Sun towards the Earth, it's a pretty small target. And I'll tell you why that matters. And here, it was only in 1958 that Eugene Parker made a hypothesis about the solar wind. And what he said is the Sun is blowing off material into space. And this is a plasma. And it's going about 1 million miles an hour. And if I am able to play this, it gives you an idea about what's happening at the Earth. And you see the solar wind battering into the Earth's magnetic field. It's actually folding magnetic field lines from the day side out to the night side. And then field lines on the night side can collapse and come together. And it almost acts as a catapult then for ions back down into the atmosphere, creating the aurora. And you would have noticed there, we're all familiar with the kind of dipole shape of magnetic field lines when you sprinkle around a bar magnet. And it didn't look like that. And because of the solar wind, the Earth's magnetic field looks much more like a windsock at an airport. And in some sense then, in a very important sense, the Earth's magnetic field is protecting the Earth from the solar wind. And so we come to this idea about space weather. And what we're talking about is conditions in the near-Earth space driven by solar activity. And so there are two kinds of events on the Sun that are very important. One is everybody talks about flares because it's an easy word, but it's not that important. The more important thing, and you don't say it because it's a horrible phrase, coronal mass ejections, but it's a bit like the Sun being a blunderbuss and throwing out an eruption of material into space. And if it happens to be pointed at us, then it's going to cause some damage. The second thing is a coronal hole. And at different parts of the solar cycle, then it's a bit like a lighthouse beam. If you see it today, then the Sun, when we look at it from Earth, takes about 27 days to go round. So there's a chance that when it comes back, it's still going to shine on you again. So you get recurrent magnetic storms as well as big one-off events. Okay, and we can see, I'll go a little bit more quickly now, and we can see the solar climate, if you like, cause sunspots, which is the red graph there, is showing how sunspots go up and down on an 11-year cycle. And down below, the histogram in blue shows how many magnetic storms there are at any particular time. And I've highlighted a little bit in yellow to show that often you get more magnetic storms during the declining phase of the solar cycle rather than at maximum. Why does it all matter? Well, the answer is, today, we've got lots of eggs in the space basket, which we didn't used to have. And so the big question is, what if the magnetic storm of that date happened today? And so there are all kinds of things. The hazard has always been there, but now there's a real risk because we put vulnerable pieces of equipment in a hazardous area. And so it affects people, astronauts. it affects satellites, and so we really need to take notice of what it is. And particularly important in this would be, increasingly so, would be GPS, or more generally what you call Global Navigation Satellite Systems, GNSS. But we're also vulnerable on the ground, and the big one is power distribution, electrical power distribution. And what happens is that you have a varying ionospheric current that we talked about. It creates a varying magnetic field, and that makes currents flowing the ground. And transformers are grounded, and so currents can flow into them. And these transformers have oil inside them, and they can become heaters and boil the oil. And the consequence can be loss of power. And think what would happen if all the transformers in the UK went down. It's a big deal, because you can't just go to the transformer shop and buy a new one. It costs a lot of money, and they'll say, yeah, we'll deliver it in 18 months. So very serious problem. But are we crying wolf? This is Quebec on the 13th of March, 1989, and if you've been wandering around in the early hours of the morning, that's what you would have seen at 20 minutes to 3. 5 minutes later, that's what you would have seen. So it really does happen. And so you get damage to transformers. It shut down the grid in 90 seconds, and we've also seen some effects in the UK and in other countries, and very surprisingly, even at low latitudes, like South Africa, which we wouldn't expect. And so what we've done is argue for this to be included in the National Risk Register, along with, dare I say it, a pandemic, right, as a number one risk. And I'll maybe jump a little bit now. Or maybe I won't. I'll just say one of the things I got involved in, may not be very sexy to say it now, but in directional drilling for oil. And what we did was show there are methods of adapting to the effects due to magnetic storms. And in directional drilling, you've got economic targets, you've got safety targets, and you've got legacy, to know that if you drilled a hole in the ground, where it is, in case you need to go back to it. And much more recently, then there's a big storm in May 2024, and farmers were getting very worried about their automated tractors because they were going off straight lines. And this is because they're using the GPS signals, which become more unreliable. And we know all the different applications of GPS. So during a big magnetic storm, there's a loss of precision. This is a big deal for agriculture in terms of loss of production. So to conclude, the sounds. Yeah, it is likely that sounds are heard occasionally, as John Rae said, during displays. We've got instrumental recordings for the very first time by Professor Liner, and he has produced quite plausible explanations supported by the data. I can't see any reason for there being links between the aurora and the tides. And once, say back in 1800, you could just sit back and enjoy the show. Now the aurora are also warning lights for our technological society. Okay, and so I'd like to thank various people, Howie, Tom, Callum, Alan, Scott, here in Orkney, and other people in the science arena that are consultants. Thank you.
We've got time for a couple of questions, so if you put your hand up, who's got the roving mic? Oh, Callum. There we go.
I'm not sure how relevant this is, but with the aurora lights and the electromagnetic fields and that, how Does that affect us, our brainwaves, when we're looking at it? Would it affect our behaviour, make us hyper or lethargic, whatever?
I don't think there's any evidence of that happening, and if you go to a science conference, there are often I haven't seen any published papers that say that it does, but again, just like the auroral sounds, you don't dismiss things, and perhaps there are people who feel that that is happening. But the question, the whole questions about human perception are quite subtle, I think, because of the way the brain works and the way that the brain can manufacture reactions. And whether that is, if you count that as causative, well, it's a little bit of a question of definition. But I haven't heard it widely reported. But another thing here is when I talked about the spectrum, I haven't seen much about whether animals react differently. So, you know, I always try to keep an open mind, but I haven't seen any positive reports along those lines.
Thank you for an interesting talk. You've said about ocean currents having an effect on magnetic fields. With the slowing up of the Gulf Stream, the current that goes all around the world, is that having an effect on magnetic fields and Earth's magnetism in general?
Well, I was actually making a remark about the remarkable fidelity with which we can collect magnetic field data from space. So Faraday's law says, you know, if you have a magnet and if you move metal beneath it, you make currents flow in it, and those currents themselves then produce a secondary magnetic field. And here, so what is happening is, as the ocean currents move through the Earth's magnetic field, some currents are induced in the oceans, and we're actually able to detect the fields that they produce in space. So there's nothing that implies a force applying, but it's just a remarkable achievement in what we're able to do by putting a magnetometer similar to that in Yesnaby in a satellite, and we can see the effects of ocean movements on the magnetic field through the secondary fields that are produced. But there's nothing slowing down the oceans or anything.
I could manage one more question before you get yourself back up the top.
I'm getting there.
Really?
It's a dated idea that perception is communicated by one sensory organ, and I wondered if any of the researchers had given thought to other perception than the ears, for feet maybe.
Well, I think yes, basically, in this sense, that we know that if we regard ourselves for a moment as instrumented, then we have the inputs from eyes, ears, all the different senses that go into one place. And so the idea of synesthesia is that you can get crosstalk between the different senses, and that's why some people see letters and numbers in terms of colour. And so there's definitely, within our processing units in our head, the ability to mix up and create a perception that is made up from the various different inputs we get from our senses. And so that's what makes us different from scientific instruments where we can stop at the point of having a high fidelity measurement and write it down, in effect. In our heads, we don't write it down, but we process it immediately. and we have the ability, and it does happen, to mix things up. I can remember, for example, just being convinced I was hearing music, but I knew I wasn't because it sounded so good. So the brain is a peculiar thing that's capable of all kinds of things. So I think if that was your question, then it's kind of a yes.
Right, I'm just going to wind up the session now. Before you leave, can we ask that you fill out a feedback form for this session? It helps us plan for next year, also helps towards funding. Now, there's been an issue with our feedback forms this year, and there continues to be one. Could you please ignore question 5 on the physical feedback form, which refers to the year 2018? All the rest of the questions are fine. Can we just thank David once again in the usual way? Thanks, David.